Okay, so today's lesson is going to be about inverse functions. So first let's start by talking about what is an inverse. So if we take a second and we read numbers 1, 2, and 3, which I will give you a second to do. What you should notice is that each one is an action and then the opposite. That one action will do something and then the other one will undo whatever that first action did. And when we have two things where they're opposites like that, one action undoes the second one, or the second action undoes the first one, we call those inverses. So we see the idea of inverses in math a lot. So some example of inverses, if we have the additive inverse, that is when we have a number and its opposite. So the additive inverse of 2 would be -2. The additive inverse of 3/4 would be -3/4. The additive inverse of -6 would be 6. And so in general, the rule is that the a and -a are additive inverses. And then multiplicative inverses are when we have two things that when we multiply them, they undo one another. So this would be 2 and 1/2, or 3/4 and 4/3, or -6 and -1/6. So a and its reciprocal are multiplicative inverses. So we see the same idea with functions, where we have functions that undo other functions. So for example, if I have a function that adds 2 to x, then its inverse, you see that little to the -1, that means that they're inverses, then its inverse would subtract 2. If I have a function that multiplies x by 4, then its inverse would divide x by 4. If I have a function, not yet, if I have a function that cubes x, then its inverse would be the cube root of x. So again, these are when one does something, the other one undoes it. So our general rule for inverses and to tell whether or not functions are inverses is that we're going to use composition, and with two functions that are inverses, when you compose them, you should be left with just your variable. The order in which you do the composition shouldn't matter. Either way, you should be left with just your variable. So here I'm going to do f of g of t, and if I'm left at the end with just a t, then these are inverses. So f of t is 2t minus 1. I'm going to take this t and I'm going to replace it with all of g. So this becomes 2 times t plus 1 over 2, and then minus 1. This 2 and this 2 will cancel. The plus 1 and minus 1 will cancel, and we are left with just a t. So the rule for functions is that if g is an inverse of f, then f is also an inverse of g, but let's check both just to be safe. So I'm going to take this t, and instead of this t, I'm going to put all of f. So 2t minus 1 plus 1 over 2. This time the minus 1 and plus 1 will cancel first, and then the 2's will cancel, and again we're left with just a t. So we would say that f is the inverse of g, or we could say that g is the inverse of f. And you don't necessarily need to use the of x notation. It means the same thing. So let's try that again on number 2. Let's check f of g of x. So I'm going to take this x and replace it with all of g. So the cube root of x minus 1 cubed plus 1. The cube root and the cubed will cancel. The minus 1 and the plus 1 will cancel, and I'll be left with just x. Or g of f of x, so I'm going to take this x and replace it with all of f. The cube root of x cubed plus 1 minus 1. Plus 1 and minus 1 will cancel. Cube root and cubic will cancel, and we'll be left with just x. Okay. Now, I'm going to graph these in my calculator, but keep in mind that f is a cubic function that has been moved up 1, and g is a cube root function that has been moved to the right 1. So you can sketch those graphs on your notes, but that's my cubic, and here is my cube root. There it is. And so if we go to the table, I have to put my table back to auto. There we go. -2, -7, -1, 0, 1, 2, 0, 1, and then 1, 2, 2, 9. I want to look at g and what happens at these values. At -7, g, which is my y2, is -2. At 0, g was -1. At 1, g was 0. At 2, g was 1. And at 9, g was 2. So notice that all of my x and y values flipped places. And if we look back at our graph and we include the line y equals x, those two lines are reflections of one another over the line y equals x. So everything that we've just said, those are all of the properties of inverses. So I want you to, on the next page, write down all of the properties of inverses. So here they are. So let's go through them together. If they're inverses, then f and f inverse undo one another. And when we compose them, we should come back just to x. If there is a point on f, then we have the flip of that point on its inverse. The graphs are reflections through the line y equals x. And since my x and my y flip places like this, then my domain and my range flip places as well. So the domain of the original is the range of the inverse. The range of the original is the domain of the inverse. Now I want you to take a second and pause this video. Make sure that you've copied all of this down, and then try example 3. Okay, so hopefully you paused it, you copied everything down, you tried example 3. Let's take a look at example 3. I would say yes, these two are inverses. And like I said before, if v is the inverse of g, then g is also the inverse of v. That's just the way that works. Inverses work both ways, not just one way. Okay, so having said that, let's talk about y equals x squared. Y equals x squared, our good old friend, the parabola. Does this have an inverse function? Well, one of the things that we said was that inverses, the graphs are a reflection of each other over the line y equals x. So if I take this and I reflect it over the line y equals x, I am going to end up with a graph that looks like this. Is that a function? No. So I know that our instinct is to say that the square root is the inverse of x squared, and it is most of the time. Square root and squared are not inverses when we think about negative numbers, because like we said before, the domain of one is the range of the other. And if we think about the domain of a quadratic, it is all real numbers, and the range is 0 to infinity. But if we think about square root, that has a domain and a range of 0 to infinity. So my range becomes my domain is my range, but these two don't match up. And that's another reason why these two, as they're given to us, are not inverses. Now we can make them inverses by restricting this domain so that it matches this range and only looking at half of the parabola. But unless we make that restriction, these two are not inverses of one another. So one of the things that we need to keep in mind is that if we have this property where we take a graph and we flip it along y equals x to get its inverse, then that means that the original graph had to have a certain set of properties in order for its inverse to also be a function. So that property is called being one-to-one. So in a one-to-one function, not only are the x's unique, but so are the y's. Because if we think about this, when we do this check on domain and range, if the range of my original becomes the domain of its inverse, or should match the domain of its inverse, then the range has to have all unique values so that when it becomes, or when it is matched to that domain, it is still all unique values. So only one-to-one functions have inverses. And to test whether or not something is one-to-one, we use the horizontal line test. It functions the exact same way that the vertical line test does, in that if it crosses more than once, then it's not a function. Only here it's if it crosses more than once, it's not one-to-one. So let's see what I mean by that. This graph would pass the vertical line test, and it would also pass the horizontal line test. So this is one-to-one. That means that it has an inverse. And while this graph would pass the vertical line test, so it is a function, it would not pass the horizontal line test. So it doesn't have an inverse. And from here on out, I'm just going to be putting yes or no. Do these things have inverses? So here, does this have an inverse? Well, my y's repeat, so no inverse. But here, all of my x's are unique and all of my y's are unique, so this would have an inverse. For this one, A, C, E, and G are all unique, so it is a function. B, D, F, and A are all unique, so it does have an inverse. R, T, V, Z all unique, so it is a function. S, U, W, U, though, does not have an inverse. Okay, so in order to find an inverse, we follow 3 steps. First, we change f of x to y. Then we swap x and y. Then we solve for y. So let's try it. We looked at this function together a couple of times when we were talking about rationals on the very last night that we were all together. The domain of this rational would be all real numbers except the place where the denominator equals 0. That's going to be my vertical asymptote. And its domain we didn't really talk about range of rationals. I will tell you that the range of this one is all real numbers except 0 because it's got a horizontal asymptote of 0. It's zeros. Remember, you set the numerator equal to 0 and solve. 3 doesn't equal 0, so it has no zeros. And for its y-intercept, we set x equal to 0, so 3 over 0 plus 1. That's going to be 3. The horizontal asymptote, is it bigger on the top, on the bottom, or are they the same? This one is bigger on the bottom, so my horizontal asymptote is y equals 0. So then to find the inverse, we say y equals 3 over x plus 1, which would change to x equals 3 over y plus 1. And then we put the x over 1 and we cross multiply. So 3 times 1 is 3, and then x times y plus 1. Now the idea here is to try to get y by itself. So I am going to distribute that x. 3 equals xy plus x. Then I'm going to subtract the x. And then I'm going to divide by this x. So y equals negative x plus 3 over x, and that is my inverse. So if we're looking at this as a rational function, the vertical asymptote would be at 0 because x equals 0. There's nothing to solve there. So then my domain would be all real numbers except 0. For the zeros, we set the numerator equal to 0 and solve. The range, well, the horizontal asymptote here is they're the same degree top and bottom, so it's going to be the leading coefficients, -1 over 1. The range is all real numbers except that -1. And then for my y-intercept, I make x 0. Can't have 0 in the denominator, so there's no y-intercepts. Now, if we take a second and we compare what we have up here to what we have down here, you should notice that everything flips places because that's what inverses do. Let's try it again. They gave me the domain for this one. It is -2 to infinity. This is a quadratic that has been shifted to the left 2 and down 3. But we only want this half of it. That way it still has an inverse. If we use the whole thing, remember, it wouldn't have an inverse. So its range is -3 to infinity. Quadratics don't have vertical asymptotes, holes, or horizontal asymptotes, so let's pretend that's not there. Zeros, so t plus 2 squared minus 3 equals 0. T plus 2 squared equals 3. T plus 2 equals the square root of 3. When I'm dealing with inverses and I'm solving, I don't use the plus or minus because we don't want both options. We only want the positive option. So t equals -2 plus the square root of 3. And then my y-intercept would be 0 plus 2 squared minus 3. So that's 2 squared, which is 4 minus 3. So that's 1. And then to find the inverse, I'm going to make this y equals t plus 2 squared minus 3. So t equals y plus 2 squared minus 3. We add the 3. And then we take the square root of both sides. So y equals the square root of t plus 3 and then a minus 2 on the outside. That would be the inverse. So that is a square root function that has been shifted to the left 3 and down 2. A square root function, normally 0 to infinity, shifted to the left 3 will be negative 3 to infinity. Range, normally 0 to infinity, shifted down 2 will be negative 2 to infinity. The zeros, square root of t plus 3 minus 2 equals 0. Square root of t plus 3 equals 2. And then we square both. So t plus 3 equals 4. T equals 1. No vertical asymptotes or holes or horizontal asymptotes on this one. Y-intercept, the square root of 0 plus 3 minus 2. So that's the square root of 3 minus 2, which, by the way, is the same as negative 2 plus the square root of 3. So it looks like for this one, we also had everything flip around, which is what we wanted to see. There is one problem on the next page that I want to try with you just because you're going to see a bunch like it on your homework. So this is find the inverse of. Now, if we rewrite this, I'm going to do this one over here. That would be y equals x plus 1 over x minus 1, which would then become x equals y plus 1 over y minus 1. And just like before, I'm going to put the x over 1 and cross multiply. So 1 times y plus 1 is y plus 1. X times y minus 1 is xy minus x. I want to get everything with a y on one side and everything without a y on the other. So I'm going to, I'll add this x over. Then I'll subtract this y over. Now I'm going to GCF out my y over here. And then I'm going to divide both sides by this x minus 1. Turns out this function was its own inverse, which doesn't always happen. It happens the most often with rational functions that they're their own inverses, but I just wanted you to see the mechanics behind how that works so that you could try those, the ones that you see on your homework. So that is the end of Unit 3. You should be able now to do all of your Unit 3 assignments, Unit 3 quiz, Unit 3 test review, Unit 3 test. If you have any questions, let me know.